Okay, so welcome everybody. This time we're going to talk about co-end calculus. So this is an extraordinarily powerful language which makes doing category theory so much easier. It basically allows us to talk about almost all of the concepts in category theory in a single kind of uniform language, and it allows us to be able to do remarkably involved derivations using some really simple symbolic manipulations. So basically what this is it's a sort of algebraic language for doing category theory. And all of these extraordinarily rich concepts that we've been talking about, these can extensions and weighted co-limits and all of these type of things, can all be expressed by these tiny little expressions in Coend calculus. And all of these great leaps of reasoning that we've been talking about can all be achieved by some very simple kind of symbolic manipulations. There's just like maybe about 4 or 5 symbol manipulation rules, and we can just mechanically use them to derive the great majority of things in category theory. It's a really, really powerful kind of idea as this coend calculus. Now, I learnt about this from Fosco Loregian's book, Coend Calculus, and I'll largely be following that. It's a wonderful book, and I highly encourage anyone listening to this to dip into it. And what I wanted to do was to try and make a kind of video to talk about the main kind of basic ideas of the Coend calculus and sort of give you the tools to get going with this. So what is Coend calculus like? I'll draw a couple of analogies. One of them is it's like algebra. So imagine what mathematics must have been like before the sort of invention of algebra, before people knew how to say things like solve 10x equals 20. Now we can write 10 times x equals 20, and we can just mechanically grind that out and find out what x has to be. But in the old times, you'd have to talk about something like that using words or using pictures, and there wasn't a uniform way of doing it. And I think now we have algebra, it makes our maths much more efficient, much more uniform, much more clear. We can do all of this fairly involved reasoning, like dividing both sides by x or whatever, without having to think about it too much, because we can just follow these symbol manipulation rules, which we've sort of verified work independently in a general kind of setting. Now, I'd say that Coend calculus is very similar. I'd say something like Coend calculus is to category theory as algebra is to arithmetic. It's a sort of algebraic way of looking at it that makes it all so much easier. Now, on the other hand, there is a bit of a challenge in getting into Coend calculus. It is a rather abstract thing. I mean, it's sort of designed to be able to express the most general concepts in category theory in a sort of uniform framework. So there is a bit of a challenge at the beginning in just sort of getting used to the way of reasoning and the kind of meaning of ends and coends. And so we're going to have to get through that. And I mean, I'd say again, it's rather like algebra. When you're a young person, just learning the basic ideas of algebra seems kind of abstract, and one has to kind of get past it. And so this video, again, like usual, I would recommend you watch this video on double speed for the first time through, so that you can see the kind of the connections. It's actually, once you get past the main definitions, it's a remarkably simple kind of type of mathematics to do, because all you end up doing is loads of symbolic manipulations based on about 4 or 5 different rules. And the really beautiful thing about this is that you can talk about all of category theory in terms of this kind of symbolic system. So you can go back and look at anything that we've talked about in this whole series, or most things in other areas of mathematics, and you can be like, well, okay, let me do the same proof but using Coend calculus. So it's a very, very beautiful kind of illuminating method. However, one has to kind of climb a bit of a hill of abstraction to appreciate it. So yes, it's very much, once one gets past the initial definitions, and there's about 3 different formulas that we have to understand, and once we've done that, everything else is like super easy. And so yes, one analogy I wanted to draw is between Coend calculus and algebra. Another one, maybe a bit grandiose, but I kind of think about this as a bit like building a computer, right? It's sort of like we want to build a computer which can allow us to do all these complicated calculations really easily. But, to do that, we have to get our soldering iron out, and we have to do some pretty involved sort of wiring and electronics and things to begin with. So maybe it's a little bit like that. So let's go. We want to talk about ends and coends, and these are sort of analogous to limits and colimits. Now, limits and colimits involve functors, but what we want to talk about are bifunctors. So what's a bifunctor? Well, this is an example of a bifunctor, this f here. And so all a bifunctor is it's a functor of this kind of form. So how do we get a bifunctor? Well, we just take a category C and take a category D, and then we just choose a functor from C op times C to D. So here C is just a category, C op is the opposite of that category, and this is the product of 2 categories. So it's going to have objects as pairs of an object from here and an object from here, and arrows as pairs of an arrow from here and an arrow from here. So let's have a look at the sort of quintessential example of a bifunctor, and that is this hom functor here. It goes from C op times C to set. We know it, we love it. It occurs at the beginning of many of my videos because hom functors are really important for category theory. They sort of tie together different levels of abstraction, right? It kind of allows us to connect things that are going on the level of objects and arrows with things that are going on the level of functors and natural transformations. So let's just recall how the hom functor works. It takes an object of this category, that will be a pair like C, C dash, and it sends it to the set of arrows from C to C dash. That's this hom set here. How does this thing work on arrows? Well, preliminary question is, well, what are the arrows in this category? And the arrows in this category, like an arrow from C, C dash to D, D dash, that's going to be a pair of an arrow V, and this arrow U op, which, U op is an arrow from C to D in C op, but really where it comes from is this arrow U from D to C in C. And so when I write U op, I just mean the sort of reversal of this arrow U, and that's going to live in the opposite category of C. And so, when we take this arrow U in the wrong direction and this arrow V in the right direction, well, U lives in C, but then U op goes sort of downwards. And then when we pair these things together, we get this arrow here, which is an arrow of this category. And then when we hom functor it, we get this sort of function here. So how does this work? Well, it's pretty simple. What we want to do is make a function which is going to allow us to translate these arrows like R from C to C dash into things that live in this set here. So what we do is we take R and then we pre-compose it with U and we post-compose it with V. And that's how this thing works. So that's the hom functor, and a general bifunctor works in a very similar way, sort of symbolically. Bifunctors are just functors. So, if you know about functors, you can figure out how these things work. Talking again about the hom functor, I might sometimes use this type of notation for the hom functor instead. So these two different things are sort of two different ways of writing the same thing. Also, often people don't write this up here, but I like to write it when I have space, because it makes it clear for me that this sort of thing is kind of like contravariant in the first argument and covariant in the second argument, and this, I think, it's really more precisely reflects what this hom functor is doing. Okay. Coend calculus has a lot to do with these bifunctors. Now, like I was saying before, we want to talk about coends and ends, and they're sort of analogous to colimits and limits. And colimits and limits are a lot to do with natural transformations. So we can think about natural transformations. I mean, bifunctors are functors too. So we could think about, what's a natural transformation beta from F to G, and we can get a definition of that. It's nothing exotic. It just means that we're going to have an arrow beta C C dash for every object C C dash in this category here, and this family of arrows are going to have to make all of these squares commute for every arrow U up comma V in this category on the left here, just for normal definition of a natural transformation. But it turns out that there's another idea, a kind of different idea, called a dinatural transformation, which is going to be more useful for us. So it's a pretty simple idea. It's kind of like a natural transformation, but only with the sort of components where C equals C dash. But don't take that too seriously. Let's just have a look at the actual definition. So when we have bifunctors F and G, which really are just functors from C up times C to D, well then we define a dinatural transformation alpha from F to G, and we write it like this, so sort of these two lines and this little circle on it. Well, this dinatural transformation of alpha consists of a load of arrows which are sort of indexed by objects of C, and they have to make certain diagrams commute. This is all very analogous to the idea of ordinary natural transformations. But what's happening here is that for every object C in our category scripty C, we're just going to have an arrow alpha C. But this is going from F of C comma C to G of C comma C. So it's kind of defined on the diagonals, if you like. And this family of arrows has to make this type of shape commute here for every arrow K from C to C dash. So let's have a look at what's going on here. What we want is that for every arrow K from C to C dash, well, if we take this arrow here, which is going to be an arrow of C op times C. So remember that F is just a functor from C op times C to D. Well, if we take an arrow in here, then of course we can apply this functor to this arrow, and that's what this is going to look like. And then if we apply the c dash component of our dinatural transformation, that gets us to g. And then we can do g on this arrow here, and we end up getting to here. So this is kind of one way around this diagram. And that composition should equal the same thing as we get when we do this kind of composition. This is just the definition of a dinatural transformation. Now, I could motivate this further, but I think it's better if I just carry on, and very quickly we'll see how all this relates to the ideas of ends and coends. So let's just remember what happens when we have just an ordinary functor, let's call it V, from a category J to a category C. And we want to find the limit of V. So what we're interested in is cones over V. So what these cones look like is as follows. We pick an apex of C, that'll just be like an object, so some object C, and then we form this constant functor. And then we consider natural transformations, alpha, from this constant functor to V. And these basically look like cones of V. So, like for example, if J looked like this category here, and then inside of our category C, we'll have this sort of, maybe these are called 1, 2, and 3, and then this would be V of 1, V of 2, and V of 3, and then a cone over this with this apex is going to look like this, and that's going to, this will be alpha subscript 3, for example. And not only are we interested in cones over this kind of diagram V, we're interested in the sort of universal cone, or the terminal object in the category of cones, because that's going to be our limit cone. Okay, this is what we do when we're thinking about limits. We think about this category that has objects as cones, and then an arrow from one cone to another is going to be an arrow from the apex of the first cone to the apex of the second cone that commutes with the sort of walls of the cone. And this is our category of cones, and the limit of our functor is the terminal object in the category of cones. Now, we're going to do exactly the same thing to define what an end is. The only difference is that we're not talking about natural transformations, we're talking about dinatural transformations, and rather than talking about cones, we're going to be talking about something called a wedge. Now, what's a cone? You recall that a cone is just a natural transformation from a constant functor to another functor V. What's a wedge? It's just a dinatural transformation from a constant functor to a bifunctor F. That's all it is. And basically everything else works analogously. So let me just back up, and I'll just sort of go through this a bit more slowly. So suppose we have a bifunctor F. In other words, suppose we have a functor from C op times C to D, and it's called F. So what is a wedge of F? Well, to get a wedge of F, we just pick an object of D. We'll call that ordinary D, and we'll refer to it sometimes as the apex of our wedge. And then our wedge just consists of a dinatural transformation from this constant functor here to F. What is this constant functor? Well, we can get it just by... What is this constant functor? Well, we can get it just by going to the terminal category, and then picking out this object D. So it's defined to make this triangle at the top commute. And what's a dinatural transformation from this constant functor to f? Well, we've already seen the definition of a dinatural transformation, but actually everything gets a lot simpler in this case. Let's have a look at our definition of a dinatural transformation again. Now, what we're doing is we're setting f to be delta d. So basically, all of this stuff at the top just gets kind of rubbed out and stuck together, and our commuting condition just ends up looking like this. Okay, so it's a big simplification, much like the condition for these kind of triangles in these cones to commute is simpler than the naturality condition. So we can be more explicit then about what a wedge is. We don't even need to refer to dinatural transformations. We can just define what a wedge is directly, and we can just say, well, a wedge just means that for every object C, we have an arrow from D to F of C, C, like this. And together these arrows have the feature that, and together this family of arrows, we might refer to them as sort of projections, thinking, in an analogous way to what's going on with cones. Well, these projection arrows just have to make these kind of diamonds commute here for every arrow K. So that's what a wedge is. It's just an apex D, a family of arrows, alpha C for every object C, such that for every arrow K, we have this kind of diamond commuting. So we have our bifunctor F, and we have these wedges over F. And it turns out that they form a category, and we call it WD of F. It's the category of wedges over F. So what are its objects and what are its arrows? Well, the objects are just wedges over F. So stuff like this, where we have an apex D and a dinatural transformation from the D-valued constant functor to F. In other words, a wedge over F with apex D. These are what the objects of this category look like. What about the arrows? Well, the arrows pretty much look like the similar to the kind of morphisms we have in the category of cones. Okay, they're just arrows between apexes which commute with these kind of projection maps involved with our wedges. So like an arrow H from this wedge to this wedge is simply going to be like an arrow H from D to D dash, which is such that for every C, we're going to have this kind of thing commuting. Where that should be an alpha dash. Okay, so that should commute for all objects C. So there we have it. That's the nature of our category of wedges. Just to cut to the chase, we're going to define an end. An end is defined just to be a terminal object of this category of wedges. And it's just the same idea as how we can define a limit to be a terminal object in the category of cones. So let's just remember how that works to motivate this stuff a bit more. So remember this idea of a cone over our functor V. Well, there's going to be a category of cones, and the objects are going to be these cones over V. They might have different apexes. Then like a morphism from one cone to another. For example, if we have a cone like this and another cone like this, then a morphism from one to the other, that's just going to be like an arrow H from C to C dash, which makes these kind of walls commute here. So it's all very, very similar. And this forms a category that we could call the category of cones of V. And we could define a limit to be a terminal object in this category of cones. It's a universal cone. Yeah, so anyway, we're more interested in ends today. And an end, as I say, is a universal wedge. It's a terminal object in the category of wedges over F. And so when we have our bifunctor, remember we started with this bifunctor, which is just a functor from C op times C to D. Well, the end of that is normally written like this. So what this is really going to be is it's going to be a sort of wedge over this bifunctor here. So, you know, we're going to have a sort of dinatural transformation from this functor here to our bifunctor. Or if you like, we have a wedge over F, and the apex of it is this sort of object here. This is going to be an object in our category D. And if we take this sort of functor, which is constantly at that object, you know, the sort of integral of F valued constant functor, well, we get this sort of universal wedge, which kind of lives with our end and gives us this dinatural transformation from this thing here to F. And so basically our end comes along with these kind of, let's call them projection maps. Okay, so we write our end like this. It's written with this sort of integral sign. And then for any object C dash, we get this arrow like this. And that's going to be an arrow of D. So there we have it. This is a way we can think about ends. And ends are very important, as are coends. And so it turns out that basically coends can just be defined in a sort of dual way. Now, as I go on in this video, I think to get the basic idea, this video is sort of self-contained, but definitely as I go later on in the video, I'm going to start referring to things from my video on all concepts. And in that video on all concepts, I actually got to a definition of a coend from a sort of totally different trajectory. I got there from can extensions and weighted colimits. But I'm going to now give you the sort of more traditional way of understanding what a coend is, and it's basically just the dual of what an end is. So you have these two different ways to think about what coends are. You know, the one I'm about to tell you and the one I already mentioned in that previous video. So let's go. We'll start again with our bifunctor F, and we talked about what wedges of F are. What's a co-wedge of F? Well, it's just a dinatural transformation, but this time it goes from F to this constant functor. You'll notice that all of this looks kind of analogous to colimits, right? Like ends are analogous to limits. Coends are analogous to colimits. Co-wedges are analogous to co-cones. So this is what a co-wedge of F looks like. It's just a dinatural transformation from F to our constant bifunctor. And so it's going to have components that look like this. And you can think of these sort of like injection maps. Okay, this is sort of analogous to what we have going on with co-products or co-limits. So this is what a co-wedge is, and there's going to be a category of co-wedges. We can see explicitly what a co-wedge is. It's just going to be basically where for every object C, we're going to have an arrow alpha C from FCC to D. And these have to be such that for every arrow K from C to C dash, we have this kind of diamond commuting. This is just unpacking what it means to have a sort of dinatural transformation from F to delta D. So this is what this means. And yes, we do have a category of co-wedges. So the objects are co-wedges, and I'm sure you can guess what the arrows are. They just go between the apexes of co-wedges and they commute with the sort of walls of these co-wedges. Okay, so like an arrow H from D comma alpha to D dash comma alpha dash is basically just going to be such that for every object C, we have this kind of triangle commuting. And so then a coend, and that's written like this. This is the coend of our bifunctor. Well, it's just going to be an initial object in our category of co-wedges. So again, this is totally analogous to the way that co-limits are defined. You know, for co-limits, you can define a category of co-cones and then say, oh, my co-limit is the initial object in my category of co-cones. And in a similar way, you know, our coend is just an initial object in this category of co-wedges of F. So really, this integral notation here is it's going to be giving us a sort of object in our category D. But, you know, there is this co-wedge that comes with it, which means that if we pick any object C dash, we get this sort of injection arrow, lambda C dash, which goes into our coend. And it's sort of analogous to the sort of injection arrows that co-products have when you're thinking about co-limits. Yeah, so this is the basic idea. Now we're going to see some other ways to think about ends and coends. In fact, we're going to see that they can literally be written as limits and co-limits of certain shapes. But I think this sort of universal wedge or universal co-wedge sort of way of thinking about them is definitely useful. And there's something else I should just say. Okay, so let me just see if I can give a tiny bit of intuition about how to think about these ends, or one way to think of them. So if we have our functor f from C op times C to D, then the end of it is written like this. F of C comma C. And you can sort of think of it as like a big product. So if we range over all the objects of C and we take the product of F of C comma C, this isn't really usually going to be isomorphic to our end, but we can get our end by taking this product and then sort of selecting a type of sub-object of this. So to a sort of first approximation, you could almost say that an end is like this product here. And in a similar way, the coend, written like this, it's not really the same thing, but it's sort of like taking the co-product over the object C of F of C comma C. Again, it's not really the same. To get the coend, we have to sort of take this co-product and then do some kind of co-equalizer. We have to sort of quotient out this co-product, stick some stuff together. But this is a nice kind of approximate way to think about this. And you can see now this notation is starting to make a bit more sense, right? Because this is like the sort of integral notation, and it kind of means that we're sort of adding up, we're varying c and we're adding f of c comma c. It's not, there's a lot of parallels with what's going on in coend calculus and ordinary calculus, but you don't need to know any calculus, and there are just these sort of similar things that are happening, which I guess motivates this integral notation here. But in a sense, if you want to think about this integral notation, I would say it's a bit more appropriate for coends when you're really co-producting things together. But anyway, this is the normal notation. This means end, this means coend. I like to think of it like when gravity is being applied, the C is going to end up falling down. You can hopefully see that we've got some kind of duality going on here. There's a sort of duality between ends and coends, and between wedges and co-wedges. So let's see if we can make this a bit more precise. So we've been thinking about arrows like G, that's an arrow of this category C. And then if we take this category C op, then the arrows in there are sort of obtained by getting arrows like G and reversing them to get this arrow G op from B to A. So that's how we take the opposite of a category. But what about a functor? Well, here's a functor f from C to D. It's going to send this arrow k here to this arrow f of k here. Now it turns out that there's this notion of being able to take the opposite of a functor. Now this isn't something that every category theorist makes explicit. Some people do this kind of thing implicitly, but I think it's good to be explicit here, because the opposite of this functor, it goes from C op to D op. So, and it's written like this. And notice that this doesn't mean an arrow that goes in the opposite direction to capital F. It means something else. So how is this opposite of this functor f defined? Well, how does it work on objects and how does it work on arrows? It works on objects the same way that f works. Okay, it sends a to f of a. So this is the same thing as this opposite of this functor operating on a. How does f op work on arrows? Well, here's an arrow of C op. This is this arrow K op. What's going to happen to it when we do this functor f op on it? Well, we're just going to apply f to K, and then we're going to reverse that arrow. So that's how this opposite functor works on arrows. So, okay, why am I mentioning this? I'm mentioning it because it's going to allow us to see the sort of connection between wedges and co-wedges pretty easily. So let's do that now. This is going to give us the main kind of duality that's going to sort of double our benefits from thinking about coend calculus. So this is the sort of fundamental result here. And what it says is that if we take a bifunctor f, then let's say we take the category of co-wedges of f, and then we take the opposite of that. Well, that's going to be the same thing as if we take the category of wedges of the opposite of the functor of f. Okay, another way you could say this, if you just do op to both sides of this equation, well, opposite of opposite is like doing nothing. So we get this. So if you like, you can define co-wedges of your functor f like this. So you get your category of wedges of f op, and then you just take the opposite of that category. And that's basically the same thing as your category of co-wedges. So this is nice because this kind of relationship here lets us relate ends and coends. So let's think about that now. So what is a coend of f? That's the kind of thing that we write like this, right? What is it? Well, by definition, it's an initial object in our category of co-wedges of f. But that's going to be a terminal object in the opposite of the category of co-wedges of f, right? Like an initial object in the category corresponds to a terminal object in the opposite of that category. So, you know, if we take opposite of both sides of this, like this, we see that actually the opposite of this category of co-wedges of f is our category of wedges of f-op. So this is also going to be a terminal object in the category of wedges of f-op. And what's that? Well, that's just an end of f-op, which is like this. So we've got this formula now. This thing here is the same as this thing here. So we can sort of swap between our expressions for ends and coends. Okay, so now we've witnessed this duality, we get to a really lovely place where we can see a different perspective on these ends and coends. Now, this relates to what I was talking about in my video on all concepts, but it doesn't rely on it. Basically, here are some more formulas for ends and coends. Here's another way to think about them, okay? Basically, if you have a bifunctor f like this, and you want to calculate the end of it, so you want to calculate this, it's the same thing as this sort of limit here. And so what this thing here is, it's the category of elements of this Hom-functor here. So, so the way this works, if we take our terminal category or trivial category, we can make this functor here, which goes into set. That just picks out the singleton set. Now let's take the comma category of that with this other functor into set, which is our Hom-functor. That's going to go from COP times C. And so if we form this type of comma category here, this is called our category of elements, and it's here. And basically the objects of this kind of category here, they're going to look like triples. So they're going to be like an object C, an object C dash, and an arrow R from C to C dash. So we could instead write such an object like this. That's going to be what an object of this category of elements here looks like. It's basically just an arrow of C. Here's another object, S, in this category. And then what's going to be an arrow from, or a morphism from this to this in this category here? Well, it's going to consist of a pair of an arrow V and an arrow U that make this type of diagram here commute. So that's going to be what we consider to be an arrow from R to S. And so that's the nature of this category here. We could call it the category of elements of the Hom-functor. We could also call it the twisted arrow category. They're the same thing. And we also have this projection functor here. And what that does, when we apply it to these objects and arrows, this R here is just going to be replaced by its endpoints. Same thing with this S here. And then this UV is going to be like UOP, V. That's going to be what the arrows over here look like. And so the idea for this thing here is that we start off with our twisted arrow category. We do this projection, forgetting about the names of the arrows. Then we do this functor F. That gives us a functor into D. If we calculate the limit of it, it's the same thing as our end. Okay, so this is a lovely idea. I put a video in the description to this. I wanted to prove this, but I also didn't want to make too many sort of lengthy technicalities introducing this. So I've added a proof of this kind of equivalence here within the description of this video. So if you have a look at the description of this video and you have a look for a video called Proof of Ends as Limits, you'll see I show this formula here, why it works. Now this is really, really nice for lots of reasons. It helps us to derive lots of our results. It connects ends to limits. I mean, in a sense, we know a lot about limits, and now ends are nothing scary, right? They're just another kind of limit. There's also a dual to this result, which looks like this. And, you know, you can get at this in a kind of dual way. It's this result which allows us to express this coend here as this co-limit. It's a little bit twisty. I mean, here we're taking the Hom functor of the opposite of C, and then we're taking the opposite again of this category of this sort of comma category here. So it's a kind of similar idea with a double twist and a co-limit. But there's a lovely thing about this, and that is that you've already seen this formula. Okay, so this formula for coends came up in our video on all concepts. So in that all concepts video, what we did was that we started with the idea of a left can extension, and then we started thinking about the you don't need to know any of this, by the way. I'm just recapping for those that remember. We started with the idea of a left can extension. Then we started thinking about the left can extension of a functor f along the Yonida embedding, and then applying that to a pre-sheaf basically gave us exactly the notion of a sort of weighted co-limit, a sort of co-limit of a functor weighted by our pre-sheaf. And then when we set our pre-sheaf to be the sort of opposite of our Hom functor, that gave us exactly this formula for a coend. This was one of the later things that we got to in that video on all concepts. And this was exactly the formula that we ended up getting, because there's this way of writing these left can extensions as these co-limits. And when we opened it up, we found that this was the formula. So, you know, we've already kind of seen this come from somewhere else. And this helps us to connect this idea of ends and coends and think of them in terms of weighted limits or weighted co-limits or can extensions or whatever. And you'll see that later on, we're going to get in the opposite direction. So you don't need to know any of the stuff that I just spoke about to do with can extensions. We're actually going to be able to express can extensions in terms of ends and coends. So what you should end up knowing eventually is kind of like why this is true. And basically you can get it just by seeing that there's a sort of equivalence between cones over this functor and wedges over f. So you should see why this is true eventually, and you get this by duality. And, you know, we're just going to use our ends and things to do lots of very cool stuff. To say briefly, I think the core idea here is that this category of wedges of f is equivalent to this category of cones of f after pi, right? And then, you know, your end is going to be your terminal object in your category of wedges. Well, that's going to correspond to your terminal object in your category of cones. And, well, that's going to be your sort of terminal cone, which is your limit cone. The limit cone of this is, of course, this limit thing, which I'm claiming is the end. So this is basically how you can get this. And then, of course, there's the whole dual idea of this, which is the way to think about the co-limit. And, and then of course the whole dual of this is this formula here for our coend in terms of this co-limit here. And it's all just sort of dual, so you can explore that as well. Now, I do encourage you, if you want to have a look at the video on all concepts and to see the sort of way that, and to see where this sort of formula comes from, because it has a kind of there's a kind of interesting way to get it, basically. So you can start with this idea of the free co-completion, and then you can sort of use that to, you're doing this sort of Yonida extension of a functor, and then you can use that kind of notion to get this notion of weighted co-limits, and then you can apply that when your sort of weighting functor is like a Hom functor, and then you can get this kind of formula. It sounds complicated, but it's interesting to see it step by step, and it gives you another way to sort of think about what these coends are. Okay, so what are we really trying to do with this coend calculus? Well, the way I look at it, I think the purpose is to try to equip ourselves with all of these tools that we can use to understand loads of different situations in category theory. And in coend calculus, these kind of things take the form of these sort of equations or natural isomorphisms relating ends or coends. And this is really the first one, and one of the most useful ones that we're going to see. And what it basically says is that the set of natural transformations from a functor f to a functor g can be written as an end. Okay, so let's just understand this a bit better. What I have on the left here, this just means the set of natural transformations from f to g. Or you could say it's the set of arrows from f to g in this functor category. Maybe some people would just write this like nat of f comma g. There's various ways to write it, but basically all we're doing is thinking about the set of natural transformations from f to g. And the point is, and it's very remarkable, that this can be written as an end. Okay? So I'm going to explain exactly how this works, but just intuitively, you can kind of think, well, this end is sort of like taking the product over C of the set of arrows from FC to GC. Now, it's not exactly as I've said before. Actually, you get your end by taking this product and then doing some kind of an equalizer to select some kind of subset of this sort of thing. But that sort of makes sense, right? Because what are the elements in a product like this? Well, you can think of them as tuples, right? For every arrow of C, you're going to have something from FC to GC. Something like, for example, the C component of a natural transformation gamma. Okay, so you can sort of think of a natural transformation as, so you can sort of think of a natural transformation as a great big tuple of arrows. You get one arrow for every object of your category C. Now, of course, though that tuple of arrows has to satisfy some conditions, it has to make some squares commute, and that's what's handled by the sort of equalizer part of the end that I'm not going to discuss. So I keep talking about this mysterious equalizer and the sort of product / equalizer definition of an end, and hopefully you'll forgive me for not mentioning that, because I think that we can do without it and see our proofs in a sort of more straightforward way. So let's see if we can prove this then. So firstly, let's be clear about what we're talking about. We have these functors f and g from a category C to a category D, And then if we form this composition here, we can call this composition d of f blank comma g blank. And so it's going to be sending an object like this to the set of arrows from f of c to g of c dash. Okay. And now what we're claiming is that the end of this kind of bifunctor, so this is really a bifunctor from, it's a functor from c up times c to set, so it's a bifunctor. Well, we're claiming that the end of this is isomorphic to the set of natural transformations from f to g. So a good question then is, what does this end look like? Okay, so it's going to end up being some kind of, it's going to correspond. So what we're going to have here is some kind of a universal wedge. Okay, we're going to have a wedge, and its apex here is basically the set of natural transformations from f to g, and there's going to be this sort of universal wedge associated with it. So what does this look like? Well, the claim is, of course, that the sort of apex of this wedge is going to be the set of natural transformations from f to g. And then this wedge is going to come along with these kind of projection maps. Okay, so for every object c dash, we're going to have this kind of, so for every object c dash, we're going to have this function lambda c dash, which is going to be sort of taking us from this set of natural transformations to the set of arrows from f of c dash to g of c dash. And how does it work? Well, it's pretty straightforward, right? Like, this is a set of natural transformations. And so lambda c dash, it just takes any particular natural transformation that's the input, let's say gamma, and then it just takes the cth component of that gamma. Okay, so this is really straightforward. Like, if we think of the elements of this as tuples of arrows that form natural transformations, then this just projects and gets the c dash components of those natural transformations. So there we have it. That's basically what this sort of universal wedge looks like. Now, it's actually pretty easy to prove that we have an end here, so I'm just going to go through a quick proof. So what we want to do, okay, firstly, we want to show that this kind of thing here is actually giving us a wedge. So we need to show that it satisfies the wedge condition. So basically, we need to show that for any arrow k from c to c dash, we have this kind of diamond commuting. But it's kind of easy to see this because basically, if you think about what the conditions mean, what they end up meaning is that this kind of square has to commute. But we know it does. So let's just go through what this means. We start off with an element of the set of natural transformations from f to g, so a natural transformation gamma. And now what we want is that this diamond commutes. So if we do lambda c on this, that just extracts the cth component. And then if we post-compose that with g of k, we get this kind of composition. And then if we go the other way around the diamond, we get this composition. And we want these two to be the same. So we want this square to commute. Well, you know, that's just exactly the naturality condition that we know that gamma has to satisfy. So this totally works. And we know that this kind of map here is indeed a dinatural transformation from this sort of constantly set of natural transformations from f to g, bifunctor to this bifunctor that gives us to this other bifunctor down here. So, okay, we're sort of halfway there. We know now that this is a wedge. All we need to do is show that it's a terminal wedge. Okay, we need to show that this is a terminal object in our category of wedges of this bifunctor here. So basically, this is our category of wedges. We know that we have this wedge here, and we want to show that it's terminal. So let's consider another wedge. And we want to show that there's going to be a unique arrow from this to this. So firstly, let's just think about the nature of a general wedge in this category. So firstly, let's just think about the nature of a general wedge over this bifunctor, so a wedge beta. So if we have a wedge beta, well, we know that then for every x that belongs to this set S that's forming the apex of our wedge, we know that, if we map, so let's just suppose we have a general wedge beta, and now we know that this kind of diamond is going to have to commute for every arrow k from C to C dash. And so if we think about what this means for a general element x of S, well, basically the way that we can think of this is as follows. We start with our x, we do beta on it, so we could call that beta C of x. I'm actually going to write the x upstairs sometime, so I'll write it as beta with the C downstairs and the x upstairs. Well, we know that once we've got this, then we have to apply this kind of lifting of our arrow under our bifunctor. And we know that that result should agree with that result. So kind of like before, what this ends up meaning is that we should have a square like this that's commuting. Basically saying that this diamond commutes is the same thing as saying that for every x, we should have that this kind of square commutes. So what does this mean? Well, the key insight here is that beta with an x upstairs and a blank downstairs is natural. It's a natural transformation. Okay. So what I mean here is that, like in this diamond, I'm showing what happens when we fix a particular x, and then we get this, and similarly we get a bxc dash on the other side, and the diagram commutes, so we have this. But now we can sort of look at this another way and say, well, what happens if we take an x in here, and then we look at all the different things that we can get by doing beta c on it, and beta c dash on it, and beta c dash dashed on it, and get all the different things, put them together, and call that resulting data structure beta of x comma blank. Well, that's just going to be a sort of tuple of arrows, and it turns out that that's actually a natural transformation. And so now we know that general wedges have this sort of form. We can make our arguments as to why this sort of wedge, we can make our argument as to why this sort of wedge with an apex as all the natural transformations from F to G is indeed our sort of terminal wedge. And basically, this is the sort of proof of it. It's pretty straightforward. So all we have to do is to show that there's this unique arrow H from S to our set of natural transformations, which is such that this kind of triangle commutes for every C. And it's pretty easy to see that, right? Because let's just define our H to send X to beta blank of X. So it's basically taking an element of S and then sort of giving us this natural transformation, which is sort of defined by the way that this wedge works. So, it's like, we have this wedge beta. So if we take an element X, then we can just apply beta, sort of vary our C and apply beta, and then we get this natural transformation beta of X blank. So that's what H does. It takes our X and it extracts the sort of natural transformation that is suggested by it, by the wedge beta. And now we can see that this kind of triangle is going to commute, right? Because we take our x, we extract the sort of beta suggested natural transformation, and then this lambda here just gives us the cth component of that. And of course, that's going to be the same thing as beta c of x, because I defined things like that. So we can see that this triangle commutes here. We can also see that this h is going to be unique. It's going to be the only sort of arrow from S to these natural transformations that would make this triangle commute for every C, because like if we used anything else apart from this H, well then we'd be sending this X here to some natural transformation other than beta of blank comma X. So let's say we sent it instead to some natural transformation delta. Well then if delta is different from beta blank comma X, well then there's going to exist some C for which delta C does not equal beta CX. And that would mean that for that C, this triangle wouldn't commute and it wouldn't work. So clearly this H defined like this is the only one that would work. So that just proves that this is a terminal object in our category of wedges, and we're done. And this is lovely. Like when we start like really applying this Coend calculus, I think you'll appreciate how cool it is that like when we see a set of natural transformations, we can just be like, oh, that's an end, because we have lots of other equations that we can then use to do further manipulations on this. And we can relate loads of things in category theory. Okay, so we've derived this equation here, and this is going to be very useful for our Coend calculus. The next one we're going to need to get there, we're going to think about something to do with limits. So let's sort of ask ourselves a question. This isn't really the focus of the video, but it'll help to motivate our derivations. So let's think about what is the functor. Let's think about what is the limit of a sort of general functor that goes from a category J to a category C. And we want to understand that. Now, understanding general functors that go into general categories can be kind of tricky, but it's pretty easy to understand the limits of functors that go into set. And so can we sort of convert this problem into a problem involving limits of functors into set? And it turns out that we can. Basically, what we want to get at for a start is this kind of formula here. So what happens is we take our functor f, and then we sort of post-compose it by this Hom functor here. So here x is just an object of C. And then we can compute the limit of this functor here into set. We know that exists, and there's a fairly straightforward way to compute limits of functors into set. And then the sort of interesting fact that's going to be useful for us for other reasons, basically acquiring rules of Coend calculus, is that these two things are actually going to be naturally isomorphic. So this is pretty easy to see if we look at it in a step-by-step way. But just why this would be of independent interest, basically, if you want to calculate the limit of the functor f, well, if you want to understand the limit of this functor f, then a good place to start is to understand like about the sort of x-shaped elements of limit of f. In other words, if you know about the arrows from x to lim f for every x, then you know a lot about the limit of f, right? For example, if you're in the category of graphs, you could take x to be a single edge, and then you understand what are the edges in this limit graph, and so on. So basically all we want to do is just understand this kind of isomorphism here. and it's pretty straightforward to get this. So firstly, what's the definition of a limit? Well, it sort of comes from this adjunction here. What's more relevant to us is that this adjunction means that we have this kind of natural isomorphism here. So basically, if we pick an object x of c, then we have that the arrows from x to the limit of f are naturally isomorphic to the cones over f with apex x. Okay, that's what this is saying. Remember that this is the sort of constant functor. So it goes like this. We start from j, and then we go to the terminal object, and then we do x, and that's what delta x is. Okay, so we already have this kind of natural isomorphism here. If this seems mysterious to you, you can look at my video on limits or adjoint functors. But yeah, we have this. Now, the key kind of result that we need to do a sort of jump in reasoning is that these cones with apex x over f, this set of cones here, is going to be naturally isomorphic to this set of cones here. So here, this is the singleton set, so it's the set with a single element. And what we're saying is that this kind of constantly singleton set functor, natural transformations from this to this kind of functor here, are naturally isomorphic to these. Now we're going to understand this in a couple of different ways. I think the simplest way is just directly, right? We just simply ask ourselves, what does a natural transformation from this to this look like? So what's going on here? Well, we have our category J, we have our category set, and we have these two functors here. So this one is our constantly singleton set functor. This one is our functor, which is giving us the arrows from x to f of blank. And we're interested in what's the natural transformation alpha from the first one to the second one. So just to sort of clarify what's going on here. So just to sort of clarify what's going on here, this functor at the bottom here, we can build it as a composition. So firstly, we're doing the functor f from j to c, and then we're doing this hom functor here. And this little triangle at the bottom commutes. So basically what we want to think about is, what does this natural transformation from alpha look like? So basically what we want to think about is, what does this natural transformation alpha look like? And well, for every object j in here, we're going to have like an arrow of this kind of form. And we just want that for every arrow k from j to j dash, we have this sort of triangle commuting here. But if we just think about what this means, well, we've got to have a single element up here. So if we apply this, we're going to get an arrow from x to f of j. So something like this. And you can see that basically the fact that this triangle is supposed to commute is going to mean that this is going to commute. So basically then, if we define beta of j to be alpha j of star, well then we're going to see that if we have like an alpha in this set, that's going to give a sort of corresponding beta in this set. And that's the nature of the sort of correspondence between these type of cones over here and these type of cones over here. Now we're going to look at this relationship between this and this in a different way in a moment, and it's sort of very different kind of we're going to get a very sort of different kind of perspective on this relationship. So I think it's good to see these things in a couple of ways. But once we've established this type of natural isomorphism here, it's pretty straightforward to go forwards, because basically we can just do this, and this is our derivation. Okay, so what's going on here? We're starting off with this set of arrows from x to the limit of f, and then the definition of limit, or the adjunction behind limit, gives us that this is naturally isomorphic to this. So we get this. Now we've just described why this type of isomorphism should hold between this and this. Now again, we can apply the definition of limit to say that this is going to be naturally isomorphic to this. But what have we got here? We've got the functions from this singleton set to this limit here on the right. And they're just going to be corresponding to the elements of this set here. So we have that this is naturally isomorphic to this. So chaining all these isomorphisms together gives us our desired result, and we're done. Okay, that's fine, but you know, from a certain perspective, I think as one understands more about this kind of Coend calculus, it gets a little bit almost distasteful to have to sort of open things up and think about, oh, you know, can we find a way to relate these type of things to these type of things, and we have to check all these conditions and so on. It's much nicer to have these kind of proofs where we're just sort of writing equations that involve kind of well-known things. And so can we actually go all the way from here to here just using equations? And we can, because now we know a bit of Coend calculus, right? We can start to sort of bootstrap. And so we've got all the way from here to here using equations, but we sort of had to do a bit of a jump of reasoning to go from here to here. That's when we had to start thinking about these cones and all that kind of stuff. So can we actually do this step in a purely kind of equational way? And it turns out that we can, because we know about ends, and we know about how to write natural transformations as ends, right? These are both just sets of natural transformations. So what we can do is we can convert these into ends. So it's really straightforward, actually. It's just exactly this kind of argument here. So here's how it goes. This is the set of natural transformations from delta x to f. Now we can write this as an end. Okay, so we just say, okay, we're sort of integrating over this j here, which is here and here. And this is just applying this result that we've already spoken about how we can think about a set of natural transformations as this sort of end over this functor here. Now, inside this integral, we can rewrite this like this. Okay, we're basically saying that, in a sense, this j at the beginning doesn't matter because this is the sort of constantly x functor. So we can rewrite it like this. We can also sort of rewrite it so that we're thinking about the functions from this singleton set into this. Hopefully you can see that this is going to be the same kind of thing as this, right? Because like the set of functions from a singleton set into another set is like the same thing as the set of elements of that other set. And now we can rewrite this like this. So again, we're just sort of replacing this singleton set here with this sort of constant functor evaluated at j. And now we can rewrite this end here. We can sort of go from this sort of, and then again, we can use this kind of natural transformations as ends kind of formula to rewrite this end here as this set of natural transformations. And this is exactly what we want to do. This is exactly this step of reasoning here. So now we can do this whole thing in a purely kind of equational way. And I really love this stuff because, each of these little isomorphism symbols is really encoding a lot of information, and there's some really beautiful kind of ideas that are just sort of hidden by these little equation signs. It's a bit, when you're learning this, I think one has to sort of suspend disbelief a little bit and get used to just doing the symbolic manipulations. But then when you get comfortable with it, you can sort of take a step back and get a sort of sense of wonder about how much is going on beneath the surface of a kind of little argument like this. Okay, so now we have this nice relationship here. We're going to use it to derive one of the most useful rules of Coend calculus. Just before we do that, let's just think about how we can remember this kind of formula. So to get a handle on it, it's a good idea to think about the case where J is just this discrete category of a couple of objects. So then when we've got a functor f from J to C, well, that's just going to be picking out a couple of objects of C. Let's call them f of 1 and f of 2. Now, what's going to be the limit of f? Well, it's just going to be f of 1 times f of 2. It's just this categorical product in this category C. And so on the left-hand side here, we have the arrows from x to f of 1 times f of 2. And we can see that they're just going to correspond to pairs of like an arrow from x to f of 1 and an arrow from x to f of 2. And that's just what this limit on the right-hand side is going to be. It's just going to be this product of these two sets of arrows. So an element of here is a pair of arrows, which by the product property is going to correspond to an arrow like this. So you can see that this relationship here encodes a lot of interesting ideas. Now, what we're going to use it for is to derive this lovely relationship here between ends. Now, I sometimes call this a sort of bracket pulling formula because basically it kind of allows you to pull this integral sign outside of the brackets. And we'll see that this is used all over the place. Now, it turns out that basically this formula here just follows pretty directly from this formula here when we write our ends here as limits. So what we have is this bifunctor h, and we're interested in these formulas for these ends here. So let's have a look at this end here on the right. Now, we've already seen that there's this formula to write an end as a limit. So we're just going to use that now. So here's our end, and here's our expression for it as a limit. So we're doing this projection functor from our twisted arrow category, and then we're applying our bifunctor here. And this is the first argument, and this is the second argument. So we can just write this a little bit more compactly like this. So we're just interested in this limit. And now we're simply going to use this formula here that we've already derived. So that just allows us to rewrite this limit like this. And now all we have to do is sort of reopen this up as an end to write it like this. And we're done. We have our derivation. And this is one of the most useful rules in Coend calculus. Now, there's also a dual to this result that we can get at. So let's think about that. Okay, so we'll start off with this functor q from c times c up to d. And now we're going to take the opposite functor to q. So that's going to have this type of form. It's going to go from c op times c to d op. And now we're going to sort of take this to be our bifunctor of interest. Actually, why don't we call it h? And then we're just going to apply the same formula that we've just derived. And it's going to give us this kind of isomorphism here. So, if you like, you can write that as a h, and then you can see that we're basically applying the same formula that we've just derived. But now let's just think about how we can rearrange this a little bit. So on the right hand side, we've got the arrows from D to this thing here in the opposite category. So that's the same thing as the arrows from this thing to this thing in the original category. So we can rewrite it like that. And this left hand side, we can also flip it around like this. And then we can sort of rewrite it like this. Now what we're using here is this notion that I derived before, which is basically that the end of the opposite of a functor is the same thing as the coend of the original functor. And so at the end of the day, what we've got is that these two things here are going to be isomorphic. Now, if we just remember where Q came from, remember that we're defining sort of H is Q op. So we can just rewrite this here as a H and rewrite this Q as a H op. Well, we have this type of relationship, and this is what we wanted. So this is our second sort of bracket pulling formula. And what this is really saying is that when we have this type of HOM relationship and we pull a kind of coend integral sign outside of the bracket, it turns into an end integral sign. So this is all sort of dual to the idea that we had before. I should say as well that a lot of authors don't bother writing opposite functors using different notations, so they might just sort of delete this op that goes there. I guess they think it's sort of clear from the context whether, a functor has been opposited or not. Okay, so now we get to our sort of final main rule that we need for this coend calculus. Like, beyond this, all we need to do is sort of use the Yonida lemma and other things that we already know, and we can just derive loads and loads of stuff in category theory. So this is the last rule that we really need to understand, but it's an important one. So basically, it's what's called Fubini's rule, and it's analogous to the normal rule that you have when you're doing integrals, that basically, like, if you're gonna, let's say you have some kind of an expression and it has two free variables, let's say it's sort of free in C and E, well then you could integrate over C and then you could integrate over E, but you could also do things in the opposite order and you get the same result. Or you could sort of imagine integrating over both variables simultaneously. And it's that kind of idea, but in terms of sort of ends and coends. So, I mean, it's a decent question to ask, what's the meaning of this, right? Because we're starting off with a functor of this kind of form. Now, what we want to do basically is to calculate a coend where we're sort of thinking of C as the thing that we're integrating over, and then integrate over E. So to do this, we really want to change this kind of functor into this kind of equivalent functor here. And you can think of this as currying, right? So if you look at my video on exponential objects, you'll note that if you look on my video on exponential objects, you'll note that this kind of functor category here is just like a exponential object in cat. So we can do this kind of currying operation. Basically, the adjunction that comes from the exponential objects tells us that these two things are equivalent to each other. So we have to sort of rearrange Q into this kind of form. So now it's a functor that has a source as C op times C. And now we can calculate an end of this. And that's going to be a functor from E op times E to D. And now we can sort of integrate this over E. We can calculate an end of this, and then we'll just get an object of D and it'll be this object of D. And the claim is that this is the same thing that you get, or it's isomorphic to the same thing that you get when you just take this and then integrate it over both variables simultaneously. Because, you know, this is, if we just sort of, we can just sort of rewrite this equivalently as a functor of this type of form. And then if we just think of this as a category, we just integrate over the objects of this category, or, you know, think of this as a sort of bifunctor from this op times this to D, and then we just apply the definition of an end, and that's kind of like integrating over both variables simultaneously. So the claim is that these two things are equivalent, and then, you know, lots of other things happen by different symmetries. Like we can also rearrange the order of integration like this, and then there's a dual to Fubini's theorem for ends, which is Fubini's theorem for coends. So if we can just understand the nature of this isomorphism, then we'll be golden. So in the description of the video, I'll put a link to a sort of more detailed argument for Fubini's rule or Fubini's theorem. I've tried to go through it in quite some detail, so hopefully that might be helpful, because I feel like it's a fairly involved result. There's a proof of it in Fosco's book, Coend Calculus. I used a different proof. The proof I used basically is using this result. So the proof I use basically is using this result, which I think is 3.8.1 in Emily Reel's book, Category Theory and Context. And basically what the theorem says is that if we have a functor f like this, then if we take the limit of it over both variables at the same time, that's equivalent to taking the limits one after the other, like this. So we should have f of I of j, and this would be f of I of j. And I kind of prefer this way of writing it. It seems a bit more precise to me. So if we have this functor f from I times j to c, if we sort of curry it, because the functor category is the exponential object in cat, we can rewrite it like this, and then we can sort of compute the limit you know, of things in this functor category using this, and then this whole composition is a functor into C, and we can take the limit of that, and you know, this is like this, and this is like this. So there's an argument for this. I go through a proof of this, and I use it together with this result. You know, that if we have an end, we can rewrite it in this sort of limit form. So it's a sort of limit where we start with our twisted arrow category, we do a projection, then we apply H. And, you know, if we rewrite our ends in this limit form, we can use this kind of limit of limit is a limit kind of thing to get Fubini's rule out. So that's the basic idea. So there's another idea which I'll just briefly mention before getting into something more substantial, because this is another idea that I used in the proof, and it seems to be a sort of reoccurring theme, is basically using these kind of arguments that involve the Yonida embedding or the Yonida lemma. And basically the idea is like this. Let's say we have a category A, and we have this expression that A of x comma B is isomorphic to A of x comma C. And I say that this is natural in X. And then from this, we can deduce that B is going to be isomorphic to C. And this seems to be a sort of reoccurring thing that we have to do. So the sort of intuitive way to think of it is that, if we have the same kind of arrows coming into B as we have coming into C from any X, then that means that B and C are the same, or isomorphic, look the same at least. But there's a more sort of precise way of thinking about this in terms of representable functors. So if I say that we have this kind of thing, natural in X, well, the right way to really say it is that these kind of contravariant Hom functors are going to be naturally isomorphic. So there's going to be a natural isomorphism phi from one to the other. Now, if we want to use this to actually get the isomorphism from B to C, well, we can do it. All we have to do is look at this and look at the sort of Beath component of this natural transformation. And that's going to have this kind of form. And then if we apply this function to an input, which is the identity arrow of B, we're going to end up getting this desired natural, we're going to get this desired isomorphism from B to C out. How can we actually see that this is the case? Well, if you watch my video on representable functors, hopefully it'll make sense. So basically, the idea is that this is a sort of representation of this functor here, and so it follows that if we take B together with the sort of element of A of B comma C that corresponds to this phi under the Yonida lemma. So in other words, if we take B and phi of B of identity of B, that's going to be an object in the category of elements of this functor here. So this is going to be an object of this. Moreover, it's actually going to be a terminal object in this category of elements. Now, because this is a contravariant functor, we write the category of elements like this. And this is going to be a terminal object of it. Also, because this identity is also giving us a representation of this functor here, the element corresponding to this, which is identity, is also going to be a terminal object of this. And so we have that this category of elements here has this as a terminal object, and it also has this as a terminal object. That means these two things are going to be isomorphic. And that means we have this isomorphism between B and C. Because, any two terminal objects in a category will always be isomorphic to each other. Okay, so we made it then. Now we have all of our rules for Coend calculus. Well, I mean, we have enough to get going, I think. We can start to use all of these to derive loads more stuff and understand like massive amounts of category theory. So let's just recap the essential rules that we're going to be using. Basically, we have Fubini's rule. So if we have a functor like this, then if we sort of do this end over both variables at the same time, that's equivalent to doing integrating over single variables, either first over C and then over E, or vice versa. And we have a similar result holding the sort of dual result which holds for ends. So that's one rule. We also have these bracket pulling formulas here. I'm not writing the H op. Sometimes people leave it out, and so will I sometimes. But yeah, this is basically allowing us to sort of pull the integral signs outside of the brackets. Outside of the brackets when we have these Hom things. And finally, we have this idea of being able to write the set of natural transformations from F to G as an end. And this is going to be all I think we're going to need. So let's now start using this stuff to derive some really interesting results. Okay then, so now we've got all these big results, let's do some stuff. In particular, let's get the Ninja Yonida lemma. So the Yonida lemma is a big deal, and there's a sort of end, and there's a sort of version of, and there are sort of versions of the Yonida lemma for ends and coends. So there's about 4 different formulas involving ends and coends, which can be thought of as kind of like the Yonida lemma. So here is one of them. And what it says is that if we have a pre-sheaf K, then it can be written like this. Okay. So it's basically allowing us to write K as this kind of end. Now, this is really just the ordinary Yonida lemma in disguise, because the ordinary Yonida lemma basically lets us express how a functor works on objects in terms of a set of natural transformations from a Hom functor. And this is kind of similar. It's just that we've changed our set of natural transformations into this end. But let's unpack this a little bit. So what are we actually doing at end of? Well, it's going to be this kind of functor here, right? So this is the second input and this is the first input, because this thing has to be contravariant in the first input because that lives there. And it's actually giving us a functor because we're leaving this blank. So this would be where this argument goes. But to understand where this formula comes from, let's actually look at what happens when we fill in this blank with an x. So what we want to show, firstly, is that k of x is isomorphic to this, naturally isomorphic to this. So how do we do it? Well, firstly, we notice that this looks like a kind of natural transformations as an end, right? So if we go back, remember when we have functors like this set of natural transformations here can be written as an end like this. And this has a similar sort of form. So we can write it to say that, well, this is just the set of natural transformations from this contravariant Hom functor to this pre-sheaf here. And then the Yonida lemma, the contravariant Yonida lemma, instantly gives us that this is going to be kx. So what we've got here is that applying this kind of functor to x, right? Because, when we do this end, we get an object of this, which is a functor from this to set. So the end, this whole thing is a functor, and applying it to x gives us kx. And moreover, this relationship is going to be natural in x. And so, we have these two functors, and, when we have this kind of thing and it's natural in x, that implies that f and g are naturally isomorphic, right? That's pretty much a tautology, right? Because to say that these things are isomorphic in a way that's natural in x means that for any x, we have a sort of isomorphism from one to the other, and it's natural. So if we sort of vary x using arrows, then it looks like a natural transformation, and that's fine. So that proves that formula. This is another kind of manifestation of this is the sort of Ninja Yonida lemma. And this one I think is more interesting. And we're going to use quite a few of our things that a few of the things that we've derived to get at this. So what we're going to do, we're going to start by writing this. So we're sort of taking this thing on the right here, and we're applying it to x, so we're putting an x here, and then we're thinking of the functions from this set here to y. Now, using our sort of bracket pulling formula, in particular using this one here, we can sort of pull this integral outside. And now if we look at this, we've got the set of functions from the product of these two sets to this set here. So we can apply currying, and we can say, well, this is the set of functions from this set here to the set of functions from this set here to this set here. So just applying currying lets us change it into this. And then what we have here is a couple of natural isomorphism. Sorry, what we have here is, we have really, well, if we think of our set of natural transformations from this functor here to this functor here, if we write that as an end, it looks just like this. So we have this isomorphism here. And now what do we have? Well, we have a load of natural transformations from a hom functor into another functor. So we just apply Yonida, Lemma, and we're done, right? We've got to here. Why are we done? Well, we're done because what we've shown here is that the set of functions from this to y is going to be naturally isomorphic to the set of functions from this to y. And this is going to be natural in y. And so that actually implies that what we're going to end up with is that this end here, kc times c of x comma c, is going to be naturally isomorphic to k of x. And this is the same kind of idea that we've seen already a few times. It's this idea that when we have this kind of thing is naturally isomorphic to this, it's natural in y, that sort of implies that this is isomorphic to this. We've seen the same kind of thing the other way around, but it works this way around too. So to see it, notice in general that when we have this type of relationship, natural in y, well, that really means we have a natural isomorphism like this, or if you like, a representation of a of c comma blank using b and phi. But then if we just sort of apply Yonida and get the corresponding element, b comma phi of identity, well, that's going to be an initial object in the category of elements of this. But also, this is another representation of this functor, and the element corresponding to this, which is going to be the identity arrow of c, is also going to be another initial object in this category of elements. This is something I covered in my video on representable functors. It's also proposition 2.4.8 in Emily Reel's book, Category Theory and Context. And so, these are both initial objects, so they're going to be isomorphic. So that proves that B is going to be isomorphic to C. So we've got this, and this is natural in X. And so that completes the proof, right? Because we can just sort of leave the X as a blank. And that's what we wanted to prove. That's our Ninja Yonida lemma. So we've got this. Let's call this equation 2. We also just got this equation 1. And there are duals to these results as well. So I'll leave you to think about the duals to these results. I'll just tell you what they are. So if we have a functor h from C to set, then the dual to 1 says that h is going to be isomorphic to this end here. And the dual to 2 is saying that H is going to be isomorphic to this coend here. So there we have it. Like, I'm taking loads of this stuff from Fosco's book, Coend Calculus. This stuff is proposition 2.2.1 in that book, if you want to have a look. Then, you know, the Yonida Lemma or Ninja Yonida Lemma, this kind of stuff is like really, really central to Coend Calculus. It's just nice that we can actually derive this kind of stuff using the rules that we've already got. Okay then, so now we're really going to start to reap the rewards of this Coend calculus. So here's a quick idea. Let's say we have a category D. Let's just say it has all products and co-products. Well, we can define the powering of D, which is an object, ordinary D, by a set S to be the co-product of D with itself once for every element of S. And then notice that we're going to have this type of relationship, right? Because, for example, when S is 2, what we're going to have here is D plus D, the arrows from D plus D to D dash. But they're just going to correspond to pairs of arrows from D to D dash. So you can see that, you know, an arrow from this co-product here to D dash corresponds to a pair of arrows, one from D to D dash and another one from D to D dash, which corresponds to a function from this 2-element set to the set of arrows from D to D dash. So in a similar way for general S, you can hopefully see that this result holds. Also, we defined the powering of D by S to be the repeated product of D with itself. And you can see that like an arrow into this repeated product is again like a function from our S into the set of arrows from D to D dash. So basically you can get at these kind of things by considering the left and right adjoints to functors. But they're called co-powering and powering, and they're actually defined like this rather than being in terms of products and co-products. You can speak about these kind of things in enriched category theory as well. Now, what we're going to do is we're going to write can extensions as ends or coends. So this is really beautiful for lots of reasons. One is that all concepts are can extensions, and now can extensions are, I'll say, coends. And so all concepts are coends or ends. And basically, the idea is that we have these formulas which allow us to write our can extension of G along F as an end or a coend, depending on which handed version we're looking at. So these results are dual to each other, and I'm just going to establish this one here, which allows us to write our left can extension as a coend. Now, just before I get into this, you may recall, like, we actually got to the idea of a coend from can extensions in our video on all concepts. So if you remember, we started with the idea of a left can extension, then we got to the idea of a weighted colimit, then we got to the idea of a coend towards the end of the video. And basically, we were able to write a coend as a weighted limit, and we're able to write a weighted limit as a can extension. So this sort of closes the circuit now, and we're able to actually write our can extension as a coend. But even nicer is that we're able to really understand what's going on here using our coend calculus, and just look at this lovely proof that we're going to be looking at. Each of these steps is something that we understand very well, and all we have to do is chain together these isomorphisms and we'll have proved this result. Might look a bit intimidating, but I swear it's really, really simple once you know the rules, which we do now. So all we have to do is think about what's the definition of left can extension. Well, let's actually think about this result here, which again we covered in the all concepts thing. The idea is that when our categories are suitably well behaved, like when E is complete and C and D are suitably small, E is co-complete and C and D are suitably small, we're going to have this adjunction here. So when we take this functor f and we form this f star thing here, which we basically, what happens with this is we have an object of this category, let's say h, and then we just pre-compose it with f. That's how f star works. So that's how f star works on objects. Well, f star is going to have a left adjoint, and that's going to be the thing that makes our left can extensions along f. And so this thing here is just this functor here applied to g living over here. So it follows then from the fact that we have this adjunction that we have this type of natural isomorphism. And we can rewrite this over here like this. So basically you could say that the left can extension of G along F is sort of defined so that we have this kind of natural isomorphism here. Natural in G and H. And so, or you could, another way to say it is that all we have to do is find a left adjoint to f star, and that will give us these can extensions. And so all we have to do to prove this result here is to show that this kind of equation here works fine if we just substitute this coend here for this. Okay, so what we want to do is to show that we have So what we want to do is to show that we have this type of isomorphism, natural in G and H. And that'll do, because that'll mean that this gives us the left adjoint to f star, and then it must be working like the left can extension. So let's do this. So we'll begin with this formula here. Now, this is a set of natural transformations from this functor to this functor. So we can write it as an end, like this. This is just expressing natural transformations as ends. Now our bracket pulling formula, this is this one here. We can use the bracket pulling to get to this. Now we can apply Fubini's theorem because we're sort of integrating over C and then integrating over X. Well, why not integrate over both at the same time? Now, if we look in here, we have this co-powering here, and we recall that we can rewrite this co-powering using this kind of formula here as this sort of thing. So we get this sort of thing. Now again, we can apply Fubini. So we can integrate over these two variables separately. Now inside here, we have this looks like the set of natural transformations from this functor to this functor. In other words, if we rewrite this stuff using natural transformations as ends, we get this. And now we can apply the Yonida lemma inside of here, which means that we'll substitute that into here, which means that we replace this stuff with this functor here applied to this input. So now we have this. And now again we apply the idea of natural transformations as ends to rewrite this as this. And we're done. We've derived this kind of natural isomorphism, and the fact that we have this means that indeed this must be an expression for the left can extension of G along F. I mean, it's maybe a bit intimidating on a first pass, but I mean, I think it's extraordinary how much is going on underneath this proof. All of these lovely isomorphisms here are carrying so much information around, and yet we're able to make this sort of derivation just by doing some really simple kind of manipulations, and there's not many of them either, you know. Every step was sort of, maybe we're applying Yonida, maybe we're doing bracket pulling or Fubini or natural transformations expressing as ends. You know, there's not many different operations that we need to do to make these wonderful derivations. Okay, so just to really nicely complete this, let's also think about weighted limits. So in my video on all concepts, I talked about weighted co-limits. I got at them from the notion of the free co-completion. Now you can also, in a dual kind of way, you can get at the notion of weighted limits from the idea of a free completion, and therefore you can write weighted limits as right can extensions. Now, just to give you a definition of what a weighted limit is, if we have a functor f from j to c and a functor w from j to set, then the limit of f weighted by w is just defined so that we have this type of isomorphism here, natural in C. And it turns out that we can also think about weighted limits in terms of ends, and basically this is our formula here. So how are we going to prove this? Well, we're just going to prove that this kind of thing here can fit in this kind of thing here, and we'll have this type of isomorphism here. That's all we have to do. So let's do it. So if we start with this left-hand side, we start with that here. Now that's a set of natural transformations. We can write that as an end. And then we can use our kind of powering idea. Remember, there's a sort of a junction based on powering, which means that this is isomorphic to this. Basically, think about this as like fj producted with itself wj times, and then you'll notice that we have you know, that these kind of arrows correspond to wj tuples of arrows from C to fj, and that's what we have here. Now what we can do is use our bracket pulling isomorphism to sort of pull this integral here outside here, and we're done, right? Because this is the right kind of form. We've shown that this is naturally isomorphic to this, and here's our end. So that's the end. Except, just to say, dualizing this, when we have a setup like this, so when we have a functor, again, f from j to c, and now we have this functor w from j up to set, well, we can speak about the w weighted colimit of f, and that's what I was discussing in my video on all concepts, and that has this sort of dual formula in terms of a coend like this. So we really connected together so many things with this stuff. And, most of this is taken from Fosco Loregian's wonderful book, Coend Calculus, and there's many more ideas in there that I haven't covered. But I feel like hopefully with this video, I've, summarized the tools that we need to get going. And you see that once we get going with this stuff, we can do a tremendous amount.